Yeah, so it's a global view, and actually this is now part of a field that is emerging, a new field, which is called planetary health. Of course, air pollution is not the only thing that affects planetary health, but this is what we're going to talk about, and also some links with climate. Now, I like to bring this image to remind us that the atmosphere is actually a very thin envelope around our planet. Most of the air is in the troposphere, the lower 10 kilometers, and then most of the rest is in the stratosphere. So 90% of the air is below 10 kilometers. And the things that we deal with is a complex mixture of things that are being emitted from natural sources, from anthropogenic sources. They mix in the atmosphere, they are chemically transformed. Gases can form particles. Actually, particles can even form gases. And things interact, also changing their properties. These are the sort of things that we deal with. Then the reaction products, either particles or other gases like acids, are being deposited, and they have effects on our biology, on the biosphere, and on human health. So how do we study these things? So there are a number of tools that we make use of. First of all, data, of course. We make measurements in the atmosphere. We use aircraft and ships. This is also that we have in common, that we collaborated on. Then we use satellite data and models. And this combination helps us to analyze, in this case, the impacts on public health. So we have a model, it's an Earth system model, and it doesn't really describe the Earth system completely. That's impossible, of course, but we think that by accounting for the atmosphere, for a lot of chemistry that happens there, the oceans and the land, we can do a decent job in studying the interactions between these things. So we have anthropogenic sources of greenhouse gases, which change the radiative balance of the atmosphere. We call radiative forcing. But actually some of the pollutants, like the oxidants, such as ozone, are also greenhouse gases. And they interact with each other. For example, the oxidants break down methane, which is a greenhouse gas. The oxidants convert gases into particles. Then we have aerosol particles that in turn can interact with clouds. So the aerosol particles serve as cloud condensation nuclei to form the clouds. And by changing the properties of the clouds and by reflecting sunlight and also absorbing sunlight, the aerosols also cause a radiative forcing of climate. Now, these radiative forcings come together and in total change the surface temperature of the planet. This we know. We have now something recorded as something like 1.1 or 1.2 degrees Celsius. But we also have the opportunity to change things. So we have a number of additional state variables mentioned here. Of course, moisture, winds, etc., but also the anthroposphere. So we have the ability through feedback such as emissions, that's up there, to change things. And this is what we need to take into account. We have a lot of information. I'm sure you're all very much aware that if greenhouse gases increase, we get a climate warming. When particles, air pollution increase, we get a climate cooling. And this is all well described in the IPCC reports. But the question that is not often being asked is what happens actually if you stop these emissions? Will everything be back to normal then? And actually, unfortunately not. Because if we stop the emissions, it will take centuries to remove the CO2, the carbon dioxide, but the particles are being removed within weeks. So that means if we could phase out fossil fuels, as we see in the upper panel, then we will be stuck with a lot of warming that is now being masked by these particles, which is about 0.5 degree. So actually that means that with 1.1 or 1.2 degrees, and this pollution which is there, we actually have already exceeded the 1.5 degree target that is being defined in the Paris Agreement. And I think this is very important to realize because it's actually quite urgent that we do something about climate change. If we could, and this is of course a theoretical exercise, remove all air pollution, it would be more than 0.7 degrees. Now, of course, this is a theoretical exercise. We will not be able to get rid of all pollution in the very short term. But even if we do it over decades, this will be the result. Now let's get into these particles a bit more. So we're talking about aerosol particles. The World the word aerosol means that the particles are floating in the air, they are suspended, and the particles that are smaller than about, say, 30, 40 micrometers have a very low, what we call gravitational settling velocity, so basically they remain suspended. They do settle, but very slowly. On the timescales that are relevant here, we call them aerosol. What is relevant for health are the smaller particles, because when you inhale them, they can actually affect your respiratory system. And the big one here, the 10 micrometer one, actually is, you cannot see with the naked eye, actually is one of the particles that determines most of the mass. For example, if you look at dust in the Arabian atmosphere. But these particles are also stuck in the upper parts of your respiratory tract. And the smaller ones, PM 2.5, so these are 2.5 micrometers diameter, they can actually penetrate more deeply. And the ones can actually penetrate very deeply. They are about 100 nanometers. We call them ultrafine. So it's important to make this distinction. And I will illustrate also why it is important to make this distinction, not only because they penetrate in a different way, but they also chemically interact with the body in a different way. If you look at the surface to volume ratio of a 10 micrometer, so these smaller particles, actually these ultrafines, they determine also the particle number concentration. So the big ones, they control the mass, and the small ones, they control the number concentration, and also the surface area. Important to remember. Then if you look at PM 2.5, this is a metric that's being used in air quality regulations, and we make distinctions among these particles. So we call them primary when they're emitted directly into the atmosphere. So dust particles or soot particles from cars or from other burning sources. Then we have primary organic particles, which are also directly emitted by combustion sources. And then we have many secondary particles. So these are particles that are formed photochemically from precursor gases, and examples are sulfur dioxide, nitrogen oxides, and then the products react with ammonia to form salts. Then we have a whole soup of volatile organic compounds, VOCs. They're being oxidized, and they usually then become less volatile, and they can form particles. If they become highly oxidized, they have a very low volatility, and they even can create new particles. So we have these gases forming inorganic and organic, we call them secondary organic aerosols. This is the SOA particles. Then we have to put all of this. There's a lot of chemistry involved here in the model. And so you see to the left, we have the emissions. There is also deposition. Some of these gases are immediately removed by deposition processes. Then we have the chemical reactions forming low volatility gases. And then there are interactions between the particles and between the particles and the gases. Some of the particles, they form clouds. Actually, most clouds evaporate again. About 90% of all clouds release the particles again in a different composition and in a different size. So these are the sort of things that we try to account for. Also the dust, the pristine dust doesn't do very much. It is important for the radiative balance. But when it becomes coated with acids, it releases, it creates salts on the surface, and then it can become, for example, effective as a cloud condensation nuclei. And then we have a number of things, public health, climate forcing, and ecosystems, which carry the impacts. Now, let's get involved into the health. So this is a question I get a lot because, you can't really see air pollution. So how can this be bad for you? What you should realize is that it's a bit like with smoking. When you smoke one cigarette, it doesn't do much. But if you smoke a lifetime long, then it does a lot. And this is also the case with air pollution. Smoking you do occasionally, but air pollution you're inhaling continuously. So per day you take about 25,000 breaths. You inhale 7 to 8 liters of air per minute. So this is about 11,000 liters per day. And if you take this on a lifetime, it's several hundreds, millions of liters of air that go through your lungs. And the continuous exposure to things that are in the air creates chronic diseases, just like smoking. Now, I mentioned that we use data. this is from a satellite product. Actually, you cannot see PM2.5 from a satellite, but you can derive it from the radiative information, the radiative flux information that is collected by the satellites. This is being combined with ground-based observations if they're available, for example, in East Asia, North America, and in Europe. And also models are being used to derive profiles. So because we are interested in stuff that happens at the surface. So this is what you get, and these data are being used by many people now. This is quite accurate. It's been quite well validated. And we now have these data for several decades, since the end of the 1990s. We also get them at the resolution, monthly resolution, so we can have seasonal cycles, and now even at 1 kilometer resolution. So this is a very good and very useful data set that we are using. However, this data does not tell us what's in the particles, and it also doesn't tell us where they come from. Of course, we see high concentrations over the deserts. It's quite obvious that we have dust there. But in general, also the interactions between the particles, and therefore we need models. So that's why we use this combination. Now, we of course compare our model with satellite observations. Actually, the main satellite that is being used for deriving this PM2.5 is called MODIS. And you can see there's relatively good agreement, but there are also differences. You see that the satellite cannot see at high latitudes. And to the right, you see our model being compared with an infrared instrument, which is more sensitive to larger particles, for example, the dust. So this is, of course, what we do. But then we also have to compare and make sure that when we look at PM2.5 from satellites and that what we produce is consistent, because we are combining these methods to derive information. And what we can do is we can use ground-based remote sensing measurements. It's called actually, NASA has established a network. It's called AeroNet. And they make the same measurements as this MODIS satellite. And so the idea is that this network helps to validate or to calibrate actually the MODIS satellite. And what you see here is a 1 year's data set of the MODIS measurements from the satellite compared with the ground-based measurements. And you see we have about 4,500 measurement data points, and it's quite noisy. Of course, this is the meteorology that is creating a lot of noise. Then if we look at our EMAG model, we see we have more than 100,000 data points because our model doesn't care whether you're at high latitudes or whether there are clouds or whatever. So we have more data points, but we also have more scatter. But what is relevant here for these studies is the long-term average. So what we are doing, we're averaging over a year. And if you go from from left to right, you see that averaging in the lower right panel is the MODIS, will give you a correlation coefficient of 0.75 about. But if we correlate our model with these data, we have a correlation coefficient even higher of about 0.8. Now, I'm not going to claim that our model is better than the satellite, but at least it gives us a confidence that we're looking at the same thing. Now, to give you some flavor, I'm not going to completely do this, but to give you an idea of how aerosol particles move around the globe, we can use the output of the model and make these animations. You see there's dust, is yellow. Actually, water is very important because we have hygroscopic salts, especially sea salt, which absorbs water, which makes the particles swell even before they form clouds. And then we have water soluble. These are the inorganic pollutants like ammonium nitrate, ammonium sulfate. We have black carbon and organic carbon. Now here we're running 2 years in a few minutes, so the weather systems are going quite fast. But it gives you an impression that how the particles are being transported across the globe and how they mix sometimes. For example, we will see over the North African and Arabian desert that there is mixing with air from Europe. So there's pollution coming in. Of course, there are also local sources. Now, I'm not going to show you everything here, but I think this will give you an idea of what we are doing and why this is relevant. So coming back to the health effects. There are a number of diseases of which the global burden of disease and the WHO, World Health Organization, state that it is being proven that they have health effects. There are a number of additional health effects which are not being considered proven but are likely. And there are also a number of pollutants that are being believed to be important, but there's not enough data to make the case. And two of them are, one of them is black carbon, the other one is ultrafine particles, and the third one is desert dust. So there's quite a lot of information that dust is not good for health. We know that it exacerbates asthma, but the proof for long-term illness is not solid enough according to the WHO and the global burden of disease. The global burden of disease is sort of like the IPCC for health, for the health community, to give you an impression. Now, the diseases that are quite clear. So here we see short-term effects at the left and the long-term effects to the right. We're going to look more into the long-term effects. But of course, there are also short-term effects, especially if pollution is very high in dust storms or in pollution events, in episodes. The long-term effects are believed to be associated with oxidative stress in the lungs. Some of the particles actually can pass the lungs and enter your body and cause oxidative stress within the body and cause what they call inflammatory responses. Now, this is not my specialty. We work a lot with public health people and also with cardiologists and other medical disciplines. So this is what I have from them. They also do, you cannot experiment with people. Actually, there are a few experiments being done with people, but this is now becoming very difficult. And so they're using mice, for example, or other rodents to study these things. And then there is a lot of epidemiological information that is being collected in what's called cohort studies. Now, we have lower respiratory infections. This is mostly pneumonia. And this is very important for children, especially in low-income countries. Many children still die from lower respiratory infections. Not here, because if you have a pneumonia, you'll get the proper treatment. But this is still a big problem in the world. Then we have chronic obstructive pulmonary disease, which is mostly bronchitis, which can also become very nasty at advanced age, especially ischemic heart disease, which leads to heart attacks. We have cerebrovascular disease, which causes strokes, which you can die from. We have lung cancer, now type 2 diabetes, and many other non-communicable diseases, as mentioned. They're not really been considered proven enough, but there are several cohort studies, for example, also on neurological disorders, such as Parkinson and Alzheimer. Now, how do we make these calculations? What we calculate is excess mortality. So you will see in the newspaper, for example, 5 million people have died from air pollution. That sounds dramatic, but it's important that you understand these terms, because 500 million people die from air pollution. Yeah, what does it mean? I mean, we all die at some point, but what is important is excess mortality. That means the mortality that has happened in a certain period that would not have happened in that period in the absence of exposure. It's actually quite simple, but it's important to understand this because we're not throwing a bomb on people when we create death by air pollution. So we have excess mortality, this delta M. It's a mortality rate for different disease categories and age classes. So we have quite a lot of information on these disease categories and at what age classes they become, relevant when they arise and also when they lead to mortality. What we also need is the baseline mortality rates. For many countries, this is good data, but not for all countries. So how many people die, basically? We need statistics there. But especially also to different disease categories. And you can imagine that not in all countries in the world, this information is of a very high level. But this is what we have to work with. Of course, then we need population data. Actually, these data are assumed to be quite good. Again, maybe there are regions in the world where they're not so good. And then what we need to make this calculation is what we call the attributable fraction. So if 10 people die, how many of these people die from air pollution or from other disorders? This is the attributable fraction. And this we calculate by using hazard ratios that we get from epidemiological cohort studies. And this has been calculated here, as you can see, HR. This is a log normal distribution. And you see that we have a hazard ratio which is dependent on the concentration. And this is being measured in cohort studies. So that all sounds quite straightforward. There's uncertainty, of course. So I have here two examples from cerebrovascular disease. For an age category, we have 5 years of age categories. We have them for children and from adults from 25 years and older. So this is for 65 to 70 years old. And we see that cerebrovascular disease has an important impact on these hazard ratios, has a high hazard ratio, but also rather high uncertainty. And you see this dashed line actually above 84 micrograms, we do not have sufficient information, so we simply extrapolate these curves. That's also something to realize. However, for ischemic heart disease, we have much better information and leading to heart attacks. And I can illustrate this here so that you understand what the hazard ratio is. If you're exposed to 60 micrograms per cubic meter for an extended period, for years, for long term, then the hazard ratio is about 2, which means that the likelihood that you will die from a heart attack will increase by a factor of 2. So also that's a quite simple concept that we can use here. And like I said, this is being measured in epidemiological cohort studies. I'm actually assuming that in Saudi Arabia, there will be areas where people are exposed to 60 micrograms per cubic meter on a long-term average. So then we can calculate these things and create these maps, and you can see where the biggest problems are. This is in Asia, Southeast and East and South Asia. Actually, about 55% of the population of the world lives in this area, but about 70% of the excess mortality related to air pollution occurs in this part of the world. But you can see there are also other red areas. So it's not so that only Asia has a problem, or South and East Asia, but there are many other areas where there is a lot of pollution and excess deaths. So our estimate, our recent estimate, this is now under review, is that 8.3 million excess deaths occur because of ambient air pollution. And this is, by the way, PM2.5 plus ozone. Now, the ozone is about 5%, so the PM2.5 causes about 7.9 million excess deaths per year. Now, there's quite a lot of uncertainty, and there's also confusion in the literature. And this is something that we try to deal with in a recent review article that you see 2 images here. So to the left is the publication year, and you can see that the early publications gave relatively low numbers. These are in millions excess deaths per year. This had to do with the fact that in these periods, the number of diseases that could be confidently associated with PM2.5 was rather small. So it's not that these studies were wrong, but the information about the number of diseases that can be confidently associated is increasing. So basically the numbers are increasing. And then you see that below there is a sort of a cluster around 4 million per year. And you see there is a cluster above, which is around between 7 or so and 10 million per year. Now, this has to do with uncertainty, but it also has to do with the methodology. And for example, the global burden of disease and the WHO choose to only account for the diseases that they find to be confidently associated. So that means the numbers are lower. But there are also many cohort studies that give us all-cause mortality. So basically, the causes that the global burden of disease is accounting for, but also a number of others, although we don't know exactly which they are. We know there are a number. I mentioned Parkinson's and Alzheimer's disease, but there's a number of others. And so that explains a large part of these differences. So it's not so that we are putting numbers in the world that are sort of inconsistent. You have to realize why these numbers are different. Now, again, let's play the trick and remove fossil air pollution and see what happens. And actually quite a lot happens. And Our recent estimates has gone up, and this has mostly to do with the fact that the use of fossil fuel has gone up. You know, we're talking in Europe and the United States a lot about becoming greener. And actually, the carbon dioxide emissions in Europe and in the United States are going down a bit. Not very strong, but they're going down. But in many other countries, they're going up. And with these emissions, also the pollution from fossil fuels is going up. So what we now calculate that from this 8.3 million per year, we can almost prevent 5 million per year when we would phase out fossil fuels. Of course, you can also clean the processes. For example, filter the particles. That would be helpful. For example, in India, there's a lot of investment in new coal-fired power plants. But in order to, be affordable, many of them do not have filters. So this is one of the reasons why the air in India is getting so polluted. And actually in China, where the trend is in a different direction, where the PM2.5 is going down, many measures have been taken, including putting filters. Now, filters help, but of course they won't solve the climate problem. So this is something I want to just put forward to you that we need to discuss. Can we or do we really need to get out of fossil, and how, and what are the consequences? But it's quite obvious that you see that many of the diseases here, if you account for all of them, I made the smaller one green to indicate what would happen if we would have a green economy. You see that the pie chart is much smaller, and there's a big difference in the excess deaths related to air pollution. Now, we also want to look a bit more into the chemistry of these particles, because what is quite interesting is that the epidemiological studies do not give us a lot of clues about which particles are more toxic than others. Basically, they tell us that PM2.5 is bad. And if you want to reduce air pollution, it would be quite helpful to know which sources to tackle first, which are the most cost-effective to tackle. So that's why we look also into the chemical information. And there is other information from toxicological studies that especially black carbon and anthropogenic particulate carbon, organic carbon, so these primary and secondary organic particles are particularly bad. And they usually assume that they are at least 2 times more toxic, or that's what comes out of these studies, than the rest of the PM2.5. So with the model, we can play a simple trick, and we can say, okay, the mortality stays the same because we know how much PM2.5 is causing, but we change the toxicity of the particles. So we have done this for anthropogenic secondary organic aerosol, primary organic aerosols. Most of this come from combustion processes. By the way, not only traffic, also biofuel use, and residential burning is important here, especially in low-income countries. And then we can make these particles more toxic and see what happens. And actually, that has quite a dramatic effect because you see that for the different source categories that we can account for. So we have biomass burning, agricultural waste burning, industry using fossil fuels. We have energy generation using fossil fuels, domestic energy use. So this is mostly biofuel use. So actually, this is carbon neutral, but it produces a lot of air pollution. Then we have shipping, waste incineration, traffic, agriculture produces ammonia, which makes particles. And then, of course, we have natural sources. So if indeed the organic particles and the black carbon particles are more toxic, then this has quite strong consequences on what priority you should associate with these sources. So you see the domestic goes up, this is the blue bars, and the natural goes down. So if this is correct, and this is something there is not sufficient proof yet, but there are strong indications that we also have to distinguish the chemical composition of these particles in terms of how toxic they are. Here's another result to indicate also the disease categories in different countries. So for example, in China, you will see that there is a lot of excess deaths from air pollution related to strokes. This is the light blue part of the pie. What you also see to the left down in the lower panels, that the lower pies, is that these brown parts are very large in Africa and also to some degree in South Asia. And this is children. They die mostly from lower respiratory illness, mostly pneumonia, because this is being aggravated by air pollution. And of course, there is a lot of not only loss of life, but also a strong loss of life expectancy when children die from air pollution. So that's why you see these large pies, for example, in Nigeria. Now, when we talk about life expectancy, we can use these global burden of disease data sets and compare our air pollution estimates with other causes or other health risks. For example, for all ambient air pollution, we compute a loss of life expectancy of almost 3 years. This is a global average. And you can see this is particularly high in Africa, not because Africa has a lot of fossil fuel pollution, but because of this effect that children die there. There's a lot of life expectancy loss. But we can compare, for example, with tobacco smoking, and if we take the global average, it's about 2.2 years. So in terms of, and this is now also being acknowledged by the WHO, is that actually air pollution is at least a similar health risk as tobacco smoking. You can say it's quite similar because some part of the air pollution is unavoidable. I mean, we cannot really get rid of much of the dust, although some of it is actually anthropogenic. And if we look at parasitic and vector-borne diseases, mostly malaria, then you see the global average is 0.6 years. And HIV/AIDS is 0.7 years. So this puts into perspective the role that air pollution plays in the loss of life expectancy. And the global burden of disease actually publishes these reports comparing different health risk factors. And even though they're quite conservative in terms of the air pollution estimates, because they only account for the, let's say, proven associations, you can see it's at number 4. So we have cardiovascular diseases. This, by the way, is for females. We have high blood pressure, which is number 1. By the way, this is really the number 1. But we also now have strong indications that air pollution contributes to high blood pressure. So I would expect that in the future, this bar, to some degree, will shift to the air pollution. When we have dietary risks, that's also quite well known, especially obesity. Then we have diabetes. In air pollution comes number 4, and we have a whole range of others. This is for males. You see tobacco smoking here is number 1, but also high blood pressure and dietary risks are very important. But also here we see air pollution at number 4. So this is, I believe, a strong message. I also now want to go into these, what we call emerging air pollutions, or WHO calls them air pollutants of emerging concern. And one of them is ultrafine particles. And there are quite a number of animal studies, animal model studies, they call it, that show that there is quite a significant impact of these ultrafines. Also because of their large surface area and their large number concentration, but also because they're very small and they can basically go around respiratory defenses that you have. So for example, if you inhale a bacteria or a particle, it's been taken care of by your immune system. They're being encapsulated and they're being removed. This is how your body works. But the small ones actually go by these respiratory defenses. And they can actually, they've done many studies. So you can find, for example, these small particles in atherosclerosis, so in plaques on your arteries. So there are already quite a number of studies that show that these ultrafine particles are important. Now, how can you deal with ultrafine particles in a global model, which is by nature relatively coarse? So this is a paper that is coming out very soon. It's being accepted. And so we have taken for different categories of emissions that we have in our model, for which it was available. So for example, domestic burning, waste incineration, agriculture, traffic, energy use, industry, size distributions of these small particles. And this is actually based on quite a large data set. So this was a very helpful data set, and the colleagues who are in Finland have helped us to use this data set. Now, if you put that in a model, our model accounts for aerosols in a modal way. It means we cannot account for each individual particle. There are two ways of doing this in models. You can have size bins, and this is actually quite expensive because in order to have a size distribution like this, you need many bins. So this is a computationally very heavy method. So what we have done, we have 7 modes. So we have 4 size modes. One is where the particles up to the right curve. These are mostly the ultrafines. Actually, these are the ultrafines. And you see these dashed curves basically describe these modes. So these vertical lines actually describe how we make the cutoff to get to these ultrafine particles. And you can see the very large ones are including, for example, the dust particles. Now, our model has a quite coarse resolution. We can run it at best at about 100 kilometer resolution. Also because we carry so much chemistry, it's quite heavy. And so I think we were also talking about running this model here. This would be quite useful if Kenya is using it. But what do we do? Because these ultrafine particles have strong gradients towards the sources, and you can actually see that here. So it's a bit, this is, by the way, not the case for PM2.5, because most of it is formed in the atmosphere, in the polluted environment, apart from the dust. But here we had to account for higher resolution. So we used some tricks. We used emission inventories, because these emission inventories, they have uncertainties, but they actually are quite good in identifying where are the sources. I mean, we know where the coal-fired power plants are, we know where the roads are, and we know where the cities are. So we can use this information, and we do this in 2 steps by using 2 different emission inventories. And you can see from the left, this is the model output, New Delhi, which is pretty coarse. Then we go to higher resolution, and this is the resolution that we can achieve at the moment. And now we have also started working on the data with machine learning, and we hope that we can improve this further to about 1 kilometer. But this is what we used in our current study. So this is about 10 kilometers, 9 or 10 kilometers resolution. This is for Riyadh. You can see what happens. Also, the model grid box around Riyadh is quite coarse. If you use these tricks, you can see that you can actually start identifying the roads to Riyadh where the ultrafine particles are being emitted. We cannot be happy with this ultimate result. We need to go to higher resolution. But you can imagine this is a global model. You cannot easily go to like 100 meters resolution. But I think there are tricks that we can use, like land use data. There's a lot of information that we could use, also from satellites, to go to higher resolution. But still, we're doing pretty okay, I would say. If you look at the model output, it's to the left. And if we correlate that with observations, this is observations from 60 stations that have been made available to us in India, in China, in Europe, in the United States. Unfortunately, we do not have stations outside of these areas. You can see the highly polluted ones are up the curve. To the left, we have our model output, and you see we already achieved like a correlation coefficient of about 0.93. But especially for the higher concentrations, the correlation is poorer. But then if we use this trick that I just showed you by downscaling to about 9 kilometers, you can see that we can even catch some of these highly polluted stations. So it's not perfect yet, and we need more data, but I think it's a good start. So next, what we can do is, okay, what does the model produce? Because there's some confusion in the field, because people assume that there is a relationship between PM2.5 and ultrafine particles. Actually, this is what I thought myself up to like a year or 2 years ago. I mean, you have very similar sources, so why should they not correlate? So we tried them to correlate them, but it actually worked very poorly. And this is also what we now see from our model results. You see the primary fraction. So this is the directly emitted fraction in percentage from ultrafine particles in the top one, and the primary fraction from the PM2.5 in the lower one. And you can see that, especially over the oceans, it's completely different. Over the oceans, we have mostly sea salt, which are PM2.5 particles, but the small ones are actually formed from sulfur compounds that are being emitted by the ocean. And of course, we see the dust is very strong in primary. We see that also, but also in some dusty regions, we see that, especially in the PM2.5, that most of the particulate material is secondary. So it's not primary emitted, but is formed in the atmosphere. And this is also the reason why we see small gradients of these PM2.5 particles, because basically they're being emitted as gases, then formed in the atmosphere, so they disperse before they become PM2.5. This is not the case for the ultrafine particles. Many of them are being emitted as small particles by combustion processes, either biomass combustion or fossil fuel combustion. Then we can also say something about the chemical composition. Actually, the reviewers were quite critical of this, and I can understand, because we have absolutely no data to test this. So this is needed. There are good instruments, like I know you're using aerosol mass spectrometry. The particles that you can see there are starting with 80 or 100 nanometers upward. Then there are some techniques to look at the very small ones, but actually the ultrafines in between. So we have to rely on our model results here to tell us something about the chemical composition. But we urgently need new techniques there. I think this is a really nice challenge for our field. We can also then make the calculations. There are a number of cohort studies. We now have two big cohort studies, one in the United States of almost 700,000 participants, and one in Europe of almost 11 million participants. So there's a quite good statistics there, and we use these. And we now estimate that the excess mortality related to ultrafine particles is about 1.3 million per year. Now, this is a very preliminary estimate, but I think it's something that we can start to work with. We can also look at the source sectors, and I'll scan through this quickly. So you can see quite big difference. Domestic is very big in Africa, and you see, for example, energy is very big in Central Eastern Europe. I want to go to the next slide to show you where are the primary sources, so the leading source sectors of these particles. We have energy, we have industry, we have RCO is residential and commercial energy use. This is basically the use of biofuels in households for burning, for heating and for cooking. Then we have traffic, and then we have, I would say, the others, which is a small category. And you can see that in Middle East and North Africa, energy is leading, traffic is number 2, and industry is number 3. The domestic are not very important here. But we can also see on the left that actually in Saudi Arabia, it's mostly traffic. So traffic is the leading source of ultrafine particles, at least according to the model, but we need more measurements here. So I'd like to summarize this. So we can estimate global excess mortality, and I hope that you now understand what this means. Excess mortality. It not means the number of people who die from this disease. It means the number of people who die prematurely from these diseases and these health risks. And we estimate about 8.3 million per year. And in the literature for PM2.5 alone, we find something between 4 and 10 million per year for the reasons that I have explained to you. It is the leading environmental health risk. So there are a number of environmental health risks, of course, with water pollution or soil pollution. But air pollution is by far the leading environmental health risk. And according to the Global Burden of Disease, it's one of the top 5 overall, with hypertension, tobacco smoking, dietary risks, and diabetes. Then we have new results on these ultrafines. They're very small. Their mass is almost negligible, but their number concentration dominates the number size distribution. And they have a large surface area. So if there are toxic things in these particles, then the area with which they can interact with your tissue, your human tissue, is relatively large. I also thought maybe there are some things of interest to KAUST to look into. I mentioned these pollutants of emerging concern, and mineral dust is also mentioned. There is proof that mineral dust is causing short-term effects, but the proof at least the confidence in the causes of chronic diseases by long-term exposure are not convincing enough yet. So we use the data, so we have numbers, but I think we need more studies, also epidemiological studies and health studies to make the case. And what's also very important is that the dust that you inhale is usually not pristine. It was quite interesting. I once gave a talk in Israel, and the example came by the door. We were looking outside, there was a dust storm. And I asked the audience, I said, what do you think this is? Is this pristine dust or polluted dust? Of course, nobody knew the answer because, we have been studying this. But actually, if it's polluted dust, then the dust particles attract water and they become little droplets and they will become white. And if they're pristine, they're yellow or red or whatever the source is. So you can actually see when the dust is being interacting with air pollutants, it changes its properties. And also the acids that deposit on the dust, they release metals, for example, from the clay minerals. And these metals cause oxidative stress. And I just want you to be aware of these things. I believe that these are important topics to study, and they're not well studied. So we have the ultrafines, a black and organic carbon. I think we have great opportunities now. We have good models. But with these models, there is no way we can get to the resolution that we want to really look into the details of health effects. But we have now these machine learning techniques. Now, we are not experts with machine learning, but we have started using them a few years ago. I'm really amazed what you can do with them. Even if you're not an expert, you just use them. You already can make enormous progress. And we have data. We have satellite data, we have measurement data on the ground, we have all kinds of measurement campaigns. Of course, we always need more, but there's something that can be done here. Do we still have a few minutes, Chuck? Because there's one thing, this is a bit of a hobby of me, because I'm very interested in the acidity of particles. And actually, you think this will be straightforward to calculate the acidity of a particle. You just make the ion balance of the particle and then you know the pH. Unfortunately, that doesn't work very well because the particles absorb water and the particles in the atmosphere actually mostly have water. That changes the properties. So it was quite a challenge to make these calculations, and of course it was even more a challenge to make these calculations since 1970. But it's quite interesting to look at these curves. So the black curves tell us, first of all, the middle panel shows us the pH, and you see there is big differences. Over the ocean, seawater has a pH of about 8. So the sea salt that is being emitted into the atmosphere has a pH of about 8. You can see that over the southern oceans. Also the dusty region, the dust is actually buffering the pH of the particles. And you can see that other areas like Asia, even Central Africa, United States, and also downwind in Europe, we have very much lower pHs, like well below 4. And you can see also the trends, and that I find also very interesting. So like in East Asia, you see that the pH is going down, and Southeast Asia, it's going down. And what you can also see what happens in the model when we take out certain components that buffer the pH. So if we take out the ammonia out of the model, you see the pH drops to even sometimes below 1. The particles are extremely acidic. And the ammonia comes mostly from agriculture. But also in some regions, and I'll put this up, like here in the Middle East, the dust is very important. But even what I really did not expect is that ammonia in this region is even more important in buffering the pH than the dust itself. So you see, if we remove the dust from the calculations, we have a pH of about 4. If we remove the ammonia and leave the dust, we have a pH of about 1. Actually, you see that it is going up with ammonia. So the ammonia is actually increasing, but the overall pH is still almost neutral. It's going down in the Middle East, and that has to do with fossil fuel use. And actually, the pH is extremely important. This is only a diagnostic, but it tells us something about the acidity of the particles. And like I said, the particles and the gases mix. And to make measurements to really see what's going on at these scales is really important. And finally, I just want to mention that we already have some really nice collaborations. We're looking at these dust pollution interactions in the model. We have looked at what it means for particle formation, for a cloud droplet formation. There we already have some nice results. And Sergei Osipov had published last year this really nice paper using the data that we jointly collected during a ship campaign, and we called the campaign Aqaba. We were sailing around the Arabian Peninsula, collecting measurements, and then analyzing these measurements with this model. And I can tell you, we had a lot of struggles in getting the emissions, I wouldn't say right, but at least in the right ballpark. So also there's a lot of work to be done to get the emissions right here. And I would like to thank you for your attention.
Thanks. Do you hear me? Do you hear me? Okay. Thanks, Jos. So the floor is open for questions. Serge, help to distribute this from that side.
Thank you. It was a great presentation. My first question is regarding the exposure assessment done with ambient air quality. And if you're thinking of including the effects of indoor air quality in this exposure assessment, it could be a highly strong factor to actually increase the numbers that we are seeing here in terms of mortality. The second question is if you're thinking of actually coupling different modeling scales to actually reach to more granularity on your data from global, regional, and then urban scale models in terms of your assessment. Thank you.
Yeah, it's good questions because especially when it's hot, we spend a lot of time indoors. Now, there are no studies in Saudi Arabia being done on this, so I think we need them. There have been studies in like Europe and in California, and I think California is the closest that I can think of compared to Saudi Arabia, because there also people basically live indoors when it is very hot. And the measurements that they've made tell us that about 70% of what you get indoors comes from outdoors. There are no homes that are really tight. So these particles are very small. They move like molecules. So basically, if there is an exchange between outside air, also when you use an air conditioning, you're sucking in outside air. If you don't filter them out, you'll get them indoors. Now, how much that is, I cannot tell you. I can tell you there are a few studies looking at indoor air quality that a large part of what comes indoors comes from outdoors. But of course, indoors adds activity. So if you're cooking on gas, for example, or whatever, you have a open fire or whatever, then of course that comes on top. And what that actually means for health, that's very poorly known. So what we do is that the relationship between outdoor air pollution and diseases is quite clear. But the actual mechanisms, how people are being exposed, if you do a lot of cycling or if you do sports outside. Actually, I was part of one study in the UK where they investigated what would be the health benefits of doing exercise outdoors as compared to being exposed to air pollution. And the net effect is that it's still recommendable to do the exercise. So that was a good message, I thought. But anyway, and the second question is, so basically I cannot answer your first question. I was trying to go around a bit. But the second one is also very relevant because we need to go to the urban scale, especially for the ultrafines. And that's where we need more data, we need measurements in the urban environment, and we need to advance our techniques also for the measure from the experimental point of view. So I'm looking at Chakchan, and he needs to develop methods to look at very small particles, or at least his community needs to.
So I have a question related to small particles. The first, it is interesting what is lifetime, because they don't deposit. They're too small to be deposited, but their lifetime probably not very long because of coagulation. So we know that a lot of ultrafine particles are produced by cooking, and we feel this kitchen. So I just remember that our sport facilities are always close to the restaurants, and with pretty strong smell of cooking. How do you think how much of ultrafine particles are on the tennis court that is close to the restaurant?
The true answer is I don't really know, but I can try to think of some things that are relevant here. So first of all, what's relevant is that we see that also from residential energy use, the exposure, unless you're very close to the indoors, basically to the source, you get exposed. But if you're not directly in the vicinity of the source, so I would say like hundreds of meters away, like the distance of your tennis court, then because the concentration at the emission source of the particles is so high that the coagulation is extremely efficient. And we also see that for measurements of biomass burning. For example, if you have a forest fire, now, first of all, very few people live near forest fires. And the second thing is that if you look at the plume that comes out of a forest fire, you see that the particles are usually somewhat larger. The smallest ones are between 100 and 200 nanometers. The reason being is that at the source you have such a high concentration of particles that they coagulate very rapidly. So I don't want to diffuse your worries, but what would worry me more is that actually cooking produces a lot of black and organic carbon, and they seem to be more toxic than other. So again, I cannot really answer your question, but there are things that one could derive here.
But you see, I see the person here.
Hello, thank you for your talk. You showed that most of the air pollution we have right now is from anthropogenic origin, so it's something that we can directly tackle. So let's assume a really bright future where we manage to tackle them all. In places such as the Middle East, we will still have the problematic of dust. So, but dust is something also really ambiguous, right? Because there are growing bodies of evidence on the role that dust plays in the environment, and for example, being the largest source of phosphorus for the Amazon, and so forth. So it plays a big role in how nutrient recycling and cycling around the world. Now, if we take the case of Saudi Arabia, we have the goal of being net zero by 2060. So we will expect that a lot of the emissions will reduce, and there is a lot of developments that rely on tourism, and people, of course, don't want to deal with dust. So there is a lot of strategies around dust, anti-dusting properties around settlements and around cities and so forth. But simultaneously, there is also a big project regarding greening the country, which will of course require natural fertilization for it to be sustainable in the long run. So my question is, what kind of strategies can a country like this follow to kind of tackle the problematic of human health regarding to dust, but also not interfere with the benefits that dust has in the environment? Thank you.
I think this would be a question to address in a report or an article, because it's such a complex question. There are many aspects here. Now, first of all, you mentioned phosphorus. I think this is probably quite relevant here, because we have a lot of desalination, a lot of cooling. So there's quite a lot of pollution being emitted that can interact with the dust. Now, Gerard told me that the Red Sea, for example, is not limited in iron. And I would assume that it is also not limited in nitrogen because we have quite a lot of nitrogen oxide emissions. But it could be limited in phosphorus. So if we have interactions of the dust with acids that come from nitric acid and sulfuric acid, it will release the phosphorus. So it actually could cause algal blooms. And this is something I don't know, but theoretically, this is certainly possible. The other thing is, I don't know how these afforestation projects, how effective they will be. Presumably, if they're successful, they will prevent some of the dust emissions. But I can imagine that it will be virtually impossible to prevent dust emissions from Saudi Arabia. So some dust will still be there. But it might make a big difference whether it's polluted dust or clean dust. The clean dust will still aggravate asthma. That's something that you cannot avoid. So children who have asthma should stay inside when there is dust in the air. So I don't think you can solve that problem. But there are many other problems that can be solved. There's one thing that I was extremely worried about is that the world thinks that hydrogen is going to save the world because there's a lot of industrial applications of hydrogen. Initially, I was extremely concerned about this because I know that even if hydrogen is being used on a large scale, you have to make it by using fossil fuels. You can actually make it by using sunlight, electrolyzers to make hydrogen out of water. But I thought if the demand increases very quickly, then people will have to use, at least in a transitional period, hydrogen that is made out of fossil fuels, mostly natural gas. So I thought leakage of natural gas would be a big issue, and also the carbon dioxide emissions would continue. But I believe that there is really a big opportunity here also for Saudi Arabia, because if you create the hydrogen, you do it at one point, you do it actually at the point where you get the methane out of the ground. That means you can make the hydrogen and you can put the CO2 back into the ground where the methane came from. So I believe that these technologies being applied in the right way will give us opportunities. And I also believe that countries that produce fossil fuels and obviously don't want to give up wealth by just turning everything off, this is not going to happen. But there are pathways towards doing things better. So this is, I think, an important message. Even though we cannot solve all the problems, we can do things in a smarter way and then, be cleaner and have a better climate.
Yes, I have two questions related to pH of aerosols. You show something related to the average pH, right? So, of course, it's understood that that's more alkaline, whereas sulfate particles are more acidic. So I guess in the atmosphere, these come as probably external mixtures. So therefore, there will be some actual very acidic particles, even though the average pH can be moderate.
That's a nasty question. You're absolutely right. This is something we cannot do well with our model because the modes are actually externally mixed, but within the mode, we assume internal mixing. So basically what we're looking here at is bulk pH. Now, the pH is actually a diagnostic. So what we want to know is acidity. But if I present numbers on acidity, nobody will know what I'm talking about. So we have diagnosed the pH. And there's another problem there. Because we use a thermodynamic equilibrium model to calculate the ion balance between the air and the particles. And there you have to make an assumption about the thermodynamic state of the particles. They're either stable or metastable. If you assume that they're metastable, they basically take up everything and everything is in the water fraction. And the dust is often in the stable state. So what we did is we used the stable state. The point I want to make, and this is really a very good point that you are making, is that if you look at these things, actually, you have to be really careful because some of the real processes in the atmosphere that occur on small scales can be actually quite relevant. So we can have alkaline particles next to acidic particles, and that will not be covered by the average pH. And the pH itself is a really bit of a tricky metric. So yeah, I mean, I should have said that. Take this with a grain of salt, a grain of. I mean, this is the best we can do at the moment, but there is a lot more work to be done.
Thank you. Another question is really on the how aerosol pH or acidity of particles affect health. So I guess, in the old days with the London, with the Pennsylvania events, people would think that, oh, it's the SO2 and therefore acidic particles causing irritations or death later. But if we are talking about chronic health impacts, even though the particle is acidic, say in the atmosphere, but as long as we inhale them, go through high relative humidity area. So I always wonder, I'd like to know your view, how important acidity of particles is in terms of health. I understand it's important in the atmosphere chemistry, all this, but actual health impacts. Yeah, thank you.
Again, this is something that's not been measured, but here we have good information. For example, when you exhale a lot of ammonia. So there's a lot of ammonia that you actually produce. So basically, this already neutralizes the particles. And you're right, the particles that you inhale, they take up water. So if they're hygroscopic, they're being exposed to a relative humidity of close to 100%. So they will swell up. That will also dilute the pH. So I don't think, from this information, that acidity itself will be very harmful because it's being neutralized when you inhale the particle.
Hello, thank you very much, Jos, for this nice presentation and overview about the health impacts of dust. Okay, I have two questions. The first one is you showed the impact of toxicity on the health impacts of toxicity. However, I'm not sure if there's any other kind of studies that consider the chemical composition of dust and how this can affect health impacts. Another question is for the ultra fine particles, which I think long time ago we used to know that ultra fine particles has short life because of coagulation or hygroscopic growth or so and so on. So my question here, I saw some high concentration of ultra fine particles over Sahara, where we don't expect to have this here. So do you have any clue what is coming from? Especially, I don't think it's coming from long range transport at that case. The last question is, sorry for this, the last one is for dust again. Because dust also has, after interacting with air pollution, it has some acids and so on, but also it have some live organs like bacteria or something. Do you think that this also can contribute to the health impact of dust, knowing the type of bacteria or how this interacts with the human body?
I'm not sure if I understand your questions all correctly. There's one point I want to make, and actually this is a result of Sergei's study, is that the concentration, the particulate concentration in Saudi Arabia is completely dominated by the dust. But the particles that really matter are small. And we're not only talking about ultrafines. Particles that are smaller, like 1 micrometer, they also penetrate quite deeply into the lungs. And they're almost exclusively anthropogenic. So the particles that you inhale here, that comes out of his study. So based on measurements and modeling, what you inhale here is of course dust, which dominates the mass. But the stuff that gets deeply into your lungs is the fine aerosol. And this is almost exclusively anthropogenic. And did I answer his question? Can you help me? You had 3 questions, so I was a bit...
I have another question. So about climate effect of cleaning of air. So you mentioned that if you get rid of aerosols, temperature will increase by 0.7, almost 0.7 degree. So and this is huge. And we actually anticipated this, and this is going on. I know that in Europe, cleaning air caused increase of temperature, and the same will probably happen in China. That is aggressively improve air quality. So so ongoing effect is expected from this?
Yeah, that's true. So that's a bit of a dilemma. So we want to clean the air to live healthier lives, but also we can do this by removing by changing energy sources from fossil to green sources, and that will remove the particles, and that will also remove the CO2, but it will also warm the planet. And this is why I showed this, because this has not been taken into account. So the 1.5 degrees is already there, but it's being masked, and actually it's mostly in the northern hemisphere. And you're absolutely right. You see big effects over China, northwestern China, for example. Sorry, northeastern China. And in Europe, indeed, we have a paper just published a few weeks ago, where we analyzed the causes of the strong warming in the Eastern Mediterranean and the Middle East. The reason in the Mediterranean region, and the reason really is that greenhouse gases are increasing. The second thing is that when you warm, you reduce soil moisture, so that's an important feedback. And the third thing is the aerosols are going down, so that is warming. So these regions are warming much more rapidly than you would expect from the greenhouse gases alone. Now, what do you conclude from this? Do nothing, do not clean the air because we don't want. What I conclude from it is that we have to get out of these fossil emissions as quickly as possible, because actually these aerosol particles are masking climate change that is there, but we're not accounting for it. We're not measuring it when we just measure the temperature. But it's there. And as soon as you stop emitting the particles, they're gone in a few weeks. And the CO2 will be there for centuries. So if you stop emitting carbon dioxide, the carbon dioxide will remain at the same level for decades, and then it will go down over centuries. So the climate warming that we have already caused by carbon dioxide will continue. But the climate cooling that we have caused by the particles will be gone in a few weeks. This is really a dilemma. So the only way of getting out of this is, take these measures in getting out of fossil emissions as soon as possible. I mean, there's no other way out.
Anything about what you are saying in terms of measurement?
Yeah, actually, that it taught us a few things. First of all, it showed that carbon dioxide emissions decreased very little. So if you look very carefully, you would see a very small dip. Most of these lockdowns actually have had an impact, especially on air traffic. The air traffic was, so we did some aircraft measurements and the air traffic emissions were gone. So also the black carbon from aircraft was gone, and the nitrogen oxides. And in some areas where traffic was being put on lockdown, that also made an impact. So actually during these periods, we had cleaner air. Yeah, but actually it was very short because most of these lockdowns were only maximum a few months. So it had a short-term positive impact on our health, but actually statistically it's almost negligible. Yeah, unfortunately.
Thank you, Jos.
But it does show that it has an effect when you do something, and that's important.
No more questions. The right-hand side was very, very quiet.
Hi, Professor. Thank you so much for your presentation. Let's say that we have PM10. We are analyzing PM10 and PM2.5. So when it comes to estimating the mortality related to both pollutants, given the relationship between PM2.5 and PM10, and also the deep penetration of PM2.5, it's enough if we use only PM2.5, or do we have to do the estimation for both pollutants?
It's quite clear that PM2.5 is more important, but actually there are many more measurements of PM10 than of PM2.5. And actually, they correlate quite well. So if you only have PM2.10 measurements, you can make an estimate of PM2.5. It's better to measure both of them. Actually, these measurements are not very difficult and they're not very expensive. And that's also why we have good data on them, because everybody makes these measurements. Every air quality network measures PM2.5 and PM10. The reason why we only look at mortality is that basically we don't have the medical data to look at what we call morbidity. So we could use the same techniques basically to calculate, what diseases are being aggravated, how people basically suffer from air pollution or other health risks. But medical data are very difficult to get a hold of. So mortality data, actually, they are there. There are plenty of mortality data. So the reason why we always talk about mortality is not because we're not interested in the diseases, but we know quite well who's dying and what they're dying of. So that's why we can use these data. But your question now, PM2.5 is more important. And actually, it could be that even smaller particles are more important, PM1, for example, because they penetrate more deeply. But we don't have the measurement networks to give us these answers. So my recommendation is would measure PM1, PM2.5, and PM10. I mean, you can never have enough information. And then we can figure these things out. It's not very expensive.
Okay, thanks very much. And let's thank our speaker for today.